All right. Good afternoon, everybody. I'm Nelson Pedreiro. I'm the Vice President for the Lockheed Martin Advanced Technology Center, our innovation labs for space. We're headquartered in Palo Alto, California, at the heart of Silicon Valley. And we've been developing technology for space systems for the past 60 years. So there are primarily two things that we do at the lab. One is to envision the future and the capabilities that our customers are going to need. And the other one that we spend a lot of time on is developing those capabilities to invent the future. So today I'm really excited to be sharing with you our vision for the future of space. We call it Space 2050. So why 2050, right? There's, of course, some arbitrariness on that, but there's also some thought behind it. We picked 2050, 28 years away. We actually started a few years back, about 30 years away or so, because it's far enough that there's really enough time to develop disruptive capabilities, and I hope to share some of those with you here in the next few minutes. But it's not so far that it becomes science fiction, right? So that's the balance here for us. So if you know anything about Lockheed Martin, you know it's all about the mission, right? And our mission is to protect, to connect, and to explore. If you look back in time, the missions that we served, the ones that we're performing now, and the ones that I'm going to be talking to you about today, which is more looking into the future, they all fall into one of these categories. So we're very, very proud of that. And what we want to do is to really build this infrastructure, this space infrastructure that is going to allow us to, in a safe manner, expand humanity beyond Earth. So let's start that journey with a video.
Purpose is found in the why of exploring what lies beyond.
InSight has passed through peak deceleration. Altitude convergence, lander separation commanded. Altitude 600 meters. Altitude 400 meters. 200 meters. 80 meters. 60 meters. 30 meters. 17 meters, standing by for touchdown. Touchdown confirmed.
NASA's InSight lander has measured the first ever Mars quake inside the red planet.
OSIRIS-REx completed a daring 2-year mission, studying and collecting a pristine sample from the asteroid Bennu. Scientists are hoping to discover insight into the origin of our solar system.
Our why inspires us to protect, connect, and explore. Today, and for generations to come.
It's really something else. I can't believe we're here.
Unearthed long ago, the why is what gives us our purpose. A mission to advance the human race into the dawn of a new space age.
Mars Base Camp, this is Lunar Control. You are a go. You're cleared to proceed to Mars. Go make history.
All right. How cool is that, right? So we start with Mars. And we're really proud to have been partners in every NASA mission to Mars. We're looking forward to be continuing that partnership well beyond 2050. You also saw OSIRIS-REx, right? If that last fall collected a sample from the Bennu asteroid about 230 million miles from Earth. Just think about it, right? That's pretty tricky, right? Quite remarkable. Requires a lot of accuracy, significant level of autonomy. I'll be talking to you a little bit more about that and further down the presentation here. But one item that is not so well publicized is that the technology used to do that sample collection maneuver, it's called natural feature tracking, and it was invented about 9 years ago or so at our labs, at the Advanced Technology Center. So we're very, very proud of that. And we have a number of examples of things that we do like that enable these kind of missions. So very, very excited about it. Then we end with a base on the moon, right, that we see as a platform for further exploration into Mars and beyond, so well aligned with NASA Gateway roadmap. So let's talk about 2050. And just before I get into that, I'll do a disclaimer here, right? When we started this exercise, we are a bunch of technologists and engineers, right? So we want a precise problem, and then we want to solve it and frame everything. There is a high degree of uncertainty, right? Even when you try to predict 2 years into the future, imagine if you go out to 2050. So I used to tell my team that, look, we're going to get about 50% of this wrong. If we're lucky, we get 50% right, and so on and so forth. And just a fun fact, almost to the day, about a month ago, Neil deGrasse Tyson came visit us and talked to the team and all of that. And I was telling him about this, and he goes, no, Nelson, he stopped me right there. You're going to get 80% wrong if you're lucky. And he's probably right on that. So let's see. Space 2050. When we started these discussions, we started on the top right of this chart here, right? We started in space, and then I said, no, let's start back on Earth, right? Because, and I'll spend a few minutes talking about what we think is going to happen on Earth, and then how to get access to space, because these things are really intrinsically related to what we're going to be able to do in space and what we're going to want it to do in space. So let's talk a little bit about Earth, right? So I'm going to date myself, but when I got out of school and so on, right, I used MATLAB and some other tools, and you have somebody doing the optics analysis, thermal analysis, and so on, and then you try to bring all that together, the design of your system. Even today, when you look today, 10, 20 years after that, there's tremendous integration on the tools, right? They really bring robustness but speed to that design analysis process, right? So when we think about 20 years ahead, 2050, so on, I expect really another quantum leap in that development, that integration, right? And that's going to have tremendous implications, not only to the engineering and our ability to develop the systems, but also the workforce, right? You're going to have space professionals that are, in a sense, different than the ones we have today. They're going to be able to spend quite a bit more time thinking about the mission and what we want to accomplish, right? And we like to talk about one-click design, right? Tell me what you want to do, and we're going to have all these integrated tools that we're able to learn from decades of experience from multiple companies and NASA and multiple organizations in designing space systems, the ones that worked well and so on, and come up with designs that are sound and that are fully automated, right? So we talk about one-click design. You really automate to a whole different level the design and analysis phase, right? The other piece that we're going to see, and we're starting seeing today, right, the mass manufacturing of spacecraft, right? I think the first production line of spacecraft was Iridium. We did many years ago, 67 spacecraft or so. Now, SpaceX is taking that to a whole new level, right? And Project Kuiper and a number of others, right? Mass-produced spacecraft, that's great. What we see in the next 20 years is a qualitative difference on that, right? It's not that you design one design, and then you build several of the same, right? That's very good. I'm very glad we're doing that right now. But what we see is basically a commoditized and customized production line where they don't need to be the same, right? Because just think about it. If you really did the one-click design that I'm talking about, if you really shrunk the time to design and do the analysis, your non-recurring becomes very, very short, and you need a way then to introduce that. So you need the manufacturing capabilities and the automation to be able to do that, right? So you're not manufacturing all the same, you're introducing new technology, you're introducing new designs. And then what's going to happen in the middle here that we think in this kind of time frame is also automation of rapid prototyping and demonstrators, right? We don't quite do that today. Right? You can mass produce, you can streamline your design, but the prototyping is still very laborious, very, very involved, a lot of the human in the loop there. We want to automate that too. So when you put this whole picture together, right, automated design, automated rapid prototyping, and then commoditized on-demand production, innovation will only be limited by the speed of ideas, right? It's not by how much it costs, because you shrunk the non-recurring. You change the whole equation between recurring and non-recurring, all the balance and so on. And innovation will only be limited by the speed of ideas. So now you're producing these, and you're inserting new technology, inserting new designs. Well, if you're doing this on a cadence, you now need to get them to space. And what we see now, talking about the middle of this chart here, is that access to space will continue the trend that we're seeing now and will accelerate, where launch costs are going to continue to come down, and they're going to continue to be readily available, right, the launch tempo. So that's going to continue. But if we're talking this long a time frame, right, 2050, we need to give serious thought of alternative ways to get our systems to space. That's why we talk about access, not just launch. Launch will be a big component of that. So the picture here, to be a little provocative, is a space elevator. But when you really look at it, it does not violate any laws of physics, right? It is, at the end of the day, a technology and engineering problem. Yes, a very hard one, right? So spin launch, space elevator, and so on. We need to take a close look at that, because what it does, some of these technologies, is totally change the way you design your space system, right? Just imagine for a moment that a space elevator, we get it to work, right? Now you have continuous access to space. There are no launch loads. Wow, think of that, right? When you look at the systems we designed and built, a lot of that is driven by this environment that you have to put this on a rocket and get it to a very quiescent environment in space. I mean, a little contradictory and so on. So it really changes the way you can do things. So we need to be thinking about that. In terms of access, we also see there's going to be a physical expansion, right? We talk a lot about LEO, MEO, GEO. We're going to expand into cislunar, and that's part of the exploration roadmap. But there's also going to be a political expansion, right? With basically every country in the world having assets in space, either of their own design, manufacturing, and launch, or that they procured and so on, so they have an interest in space. So this is going to be something that we need to be very conscientious about. And finally, we get to space, right? And then what we see on space is a continuation and an acceleration of proliferated systems. This will drive the need for autonomy, right? These large constellations, they need to operate autonomously. We've seen in the news and so on, there's a lot of concerns about collision and so on. And we also see on-orbit services, right? On-orbit manufacturing, refueling, repair, some level of assembly also in this kind of time frame will be happening in space. We see the commercialization of space, that NASA is playing such a key role right now in fostering and developing. And we see, in addition to advances in solar power and so on, we see also alternative to that, right? Which is nuclear power and propulsion will be key enabling technologies for space. We're going to need more bandwidth, and I'll be talking to you a little further down the road how we think we're going to get that kind of bandwidth that we're going to need. Because when you really think about what's going to be happening in space and all this expansion, the concept of space infrastructure becomes then very, very critical, right? Refueling of spacecraft, debris remediation, communication. Communication should be a backbone and infrastructure that if somebody has a new idea for a space system and they want to put a constellation up, they can tap into this kind of infrastructure that should be readily available. Power. Think about power, right? If you have nuclear power and you can do power beaming, it changes a little bit the way, or it may change very radically the way you design systems. We also see the continuation of, when you think about exploration, more scientific exploration in deep space, we see the continuation of that. And with the ability to build and align optical systems in space and build large structures in space, we're going to be able really to go beyond what Hubble and James Webb Space Telescope are doing and have really large apertures in space that will allow us to search for life and to further understand the origins of the universe. So we see all of those things coming together as a future for space. So what I'd like to do next is talk about different broad mission areas and go into a little bit more of a texture, give you a little bit more of a narrative here on what we think is going to happen in this kind of time frame, the vision. And then I'll follow that up by one or two examples of technology that we're working right now. So I'm going to be showing you stuff that's half done, right? These are technologies that we're developing right now, but we believe are very breakthrough, and we have, I'll share with you what we have accomplished so far. There's a way to go, right? Some of those maybe will take all the way to 2050, but some of those will not. But the point is, for some of these enabling technology, we need to start working on them right now, and we are doing exactly that. So, remote sensing. First thing that strikes you when you look at this picture is, well, where are my solar arrays? Where's my optics, right? My primary mirror, my secondary mirror structure. I mean, these things are pancakes. How is this really going to work? And so on and so forth. So what we're trying to illustrate here, and again, I'm not trying to imply that we're going to eliminate all of that, right? There will be a place for solar arrays. There will be a place for the regular optical systems, the way we've been designing them since Galileo and all of that. But there will be, there is a need, and there will be quite a bit of systems that look and operate quite differently, right? So systems like this, they can have their onboard nuclear power, or you can power them by a central power beaming unit, right? And so on, and they're doing interferometric imaging and whatnot. They can also be reconfigurable, right? You can bring a lot of these apertures together and have a different form factor that is more suitable for a particular mission versus another mission, so on. So we envision 2050 a remote sensing area, a mission area that is totally different than what we have today, right? We are going to have persistent coverage of the entire Earth, right? And it's persistent, it's all the time, right? So what can we do with that? We can do a bunch of different missions. I'll talk a little bit about that, but just think about it. The other day I was thinking about this. We operate the Space Dynamics Observatory AIA, Atmospheric Imaging Assembly, which is a sun-observing instrument for NASA. Out of that instrument alone, we get 2.5 terabytes of data a day, right? And we use algorithms and so on to look at features and then provide those pointers to the scientific community so they can look at features like a coronal mass ejection or some activity on the sun that are areas of interest. I mean, it's just a vast amount of data, right? When you think of something like this, it's going to be orders of magnitude larger, right? So collecting the data is one part of the equation. What we're really going to need here are automated AI agents, machine learning, pattern recognition, so on, that really distill that data into information, provide that to the end user. So we are going to have that too. We're going to be able to track every object on Earth and every object in space. And guess what? We need to do that, especially for objects in space. We need to have understanding what their capabilities are, where they are, and so on. What's going to help us do that are enhanced and novel sensor technologies. Quantum sensors, interferometric sensors, they are going to enable us to do those kind of things, as well as the AI ML part of that, right? Be able to deal with this vast amount of information. On the aspect of remote sensing that is more related to deep space exploration, looking at the universe and so on, we're going to be able to assemble, as I mentioned, these very large space telescopes and so on, these very large structures, right? Assemble, align them in space, and operate from there. So this is some of the things that we see in 2050. Let me share with you a little bit about technologies. I love this one, an imaging computer. So what we want to do here is pretty radical, right? We want to eliminate the telescope from an optical imaging system, right? So since Galileo, we've been using lenses and mirrors, right? And you collect your light, and you focus, and you image on the focal plane, and that's the way we do it. It works well, right? So why the heck would we want to change that? There is a different way to do imaging. It's interferometry, right? The radio astronomers have been doing that for decades. In fact, recently, interferometry was used to image a black hole in our own Milky Way. But what we're doing here is radically different. And it's taken interferometry in a whole new direction, right? What we're talking about here is a solid state array with thousands of lenslets that collect the light. And that light is interfered on the back by combining different pairs of these lenslets using a nanostructured interferometric array. And then you calculate from the interferogram patterns, you calculate the image. So you're imaging on the pupil plane. Why would we want to do that? 1 to 2 orders of magnitude reduction in mass and volume. That's one. That alone would justify it. But more than that, it totally change your flow when you're developing these systems, right? When you develop optical systems or remote sensing systems today, the whole process of assembly, integration, and test, right? So you have a very sophisticated way to build your optics and all of that. When you assemble it and you align it, extremely complex, right? And that's further down the line. Here, what we're doing, we're shifting the complexity to the manufacturing portion, which is early in the process. And it's done basically in a very controlled environment, on a semiconductor kind of factory, kind of environment, right? So we've demonstrated this first through analysis, then through in the hardware, in the laboratory, and we're working with NASA now on 2 missions. One is a solar observing mission, the other is an Earth science mission. Very excited about this technology. The second technology has to do with controls, right? Vibration controls and so on. When you have these optical systems, you can't just take care of the optics, right? Make the optics large, which gives you a high resolution, make it pristine, right? Which again gives you improved image quality and so on. You also need to be able to point these systems very precisely. And you need to be able to keep them very stable, right? But on a spacecraft, generally we have thrusters. We have reaction wheels. We may even have control moment gyros, depending on the kind of mission that you're trying to do. You have thermal snaps that happen on the structure, and all of that create mechanical vibration that perturb your optics, right? So you may have this pristine optics, but your imaging, your seeing, may be limited by the mechanical stability of this system, right? So what the team came up with here, they call it disturbance-free payload. It's pretty cool. If you look at this picture here, in this picture of real hardware, it hangs from the ceiling on two separate cables because we have to deal with gravity. The part on the front, it's like a telescope, and just on the back of the telescope is what would be like a science instrument assembly, right? And then you see a little gap. Do I have a laser here? Then you see a little gap here between the instrument bay and the spacecraft itself. And these two bodies are physically separated. There's no mechanical contact between them. But then you couple them using non-contact actuators, so voice coils, like what you have on the sound system in your home, except that these are specially designed voice coils. And what it allows you to do is to basically apply forces and torques on this payload so you can point it very precisely where you want it to look, but you isolate all the vibration, right? If you do wireless power transfer and wireless data transfer between the spacecraft and the payload, then there's really no physical connection because you don't even need the cables, right? So what this does, and you see the animation on the right, is a state-of-the-art isolation system on the top. And what we're showing here is wavefront error in, I don't know, maybe nanometers or something like that. But what we're having here is 100 to 1,000 times improve in isolation system, right? So it really allows you to have very precise, very quiescent payloads or sensors observing what you want to observe. It also, if you look at the other way, right? If you do the equation the other way, it allows you to, you don't need to be very quiet on your bus, right? You can have your reaction wheels may be a little bit unbalanced and so on and so forth. It lowered the requirements on your bus. So this interface can be made modular. The team is now, we've demonstrated this in the lab, and we measure 60 dB plus isolation broadband. The team now has designed a modular interface and is going to demonstrate that on a CubeSat. So it can be made also very compact, right? So if you take even a leap and you think ahead and you look at those pancakes that I showed you 2 slides ago, back, and if you have these interfaces, now you can bring them together and you can precisely control the figure of a much larger system, right? So very, very exciting technology. Let me shift a little bit and talk about communications. It almost doesn't matter which mission you're going to do. Communications is paramount, right? It's one of these things that you have to have. It's the infrastructure, right? You need to have reliable, trusted communications, right? We use that today to navigate. We use that for timing our banking systems and so on. If you look at 2050, that's going to be even more critical that we continue to do all of that. So with this proliferation of systems and the augmentation, the much larger amount of data that we're going to have to deal with, we're going to need more bandwidth, right? And we're going to need secure, unbreakable, truly secure communication. So, surprise, surprise, quantum communications comes to help, right? And just a couple points I want to make. Generally, when you talk about quantum communications, we immediately associate that with security, right? Quantum key distribution is going to have truly secure communications. Yes, that is true. That's been demonstrated by many organizations in the US and abroad. We've demonstrated that too. The problem today is that when you look at the architecture in these demonstrations that are being done, they do not scale to the bandwidth that you would need for this kind of communication system, right? We need to be doing something different here. And the next chart I'll show you some things that we're doing that are gonna address that problem. The other thing that you see that's different on the spacecraft, right? It's missing the solar arrays too, so power beaming. The network is fully integrated. So the reliability and resilience of this system comes by the numbers, comes from the architecture, not necessarily by the reliability of each spacecraft per se, right? So you could lose one spacecraft, 10, 100, maybe more, and the performance of your network is going to degrade gracefully. That's exactly what we want. And remember, we talked about we're launching these on a cadence, and we're upgrading technology. So in a sense, who cares if you lose a few of those? So in 2015 at the Goddard Symposium, it was the first time I used the term disposable spacecraft, and I can tell you, a lot of eyebrows are, what are you talking about, right? It makes no sense. That's what I'm talking about, right? It's not that we wanted to dispose of the spacecraft, but it's that the resilience is in the architecture. If you're producing, you squish the cost to produce, right? The non-recurring, the recurring, and you're launching on a cadence, it really doesn't become the pinch point, right? That each one of these spacecraft do not need to last for 10, 20 years as we've been doing, for quite some time. So very, very exciting area also. So first technology, quantum communications. Of everything in this chart deck, this is the area that I'm most excited about, right? Our team has come up with an approach and an architecture that allows quantum communication to not only to be escalated to high bandwidth communications as we have today, but actually to go way beyond that. And we need it, right? Think about all those data that we agreed, or maybe I assumed you agree with me, that we're going to be collecting, right, with remote sensing and other mission areas and so on. And we need to be able to communicate reliably and so on. So it is secure, right, through quantum key, this distribution. And there are basically three key breakthroughs that the team accomplished to do this. The first one really has to do with energy density or information density. So think about bits per photon, right? And the way the team did that is by multiplexing, doing temporal, multiplexing in time, multiplexing in frequency, spectral multiplexing, and multiplexing spatially, spatial multiplexing. So the picture here on the left shows a vortex beam, and the pictures on the center show a thin film optics faceplate that is used to do this spatial multiplexing on this beam. The picture on the very center is a single photon Geiger mode detector that can be used to detect single photons and retrieve the information that is multiplexed temporally, spatially, and in frequency. And the picture on the right is a flight demonstration that we're proposing to do in that. So I told you about the first one, which is the multiplexing. The second one is super additivity. And why that is important is to basically lower the noise floor so that these systems become practical, right? That you can communicate not only at night, but in daylight, right? And you can communicate not needing an excessive amount of energy to do that. And the third one is the use of non-classical sources. And this has been possible through significant investments of the US government and waveguides that are near perfect waveguides, right? So these three things brought together allows us to do that. And very, very excited about this. This has been demonstrated in the laboratory. The team is, as we speak here, they've been on a field test for 2 weeks. They have another week to go. And there's another field test planned for the fall, again on the ground. Right? And we see that in 2 years down the road, we'll be able to do a flight demonstration of it. And this system does scale to very high bandwidths. It will give us at least an order of magnitude improvement in bandwidth to what we have today. Very excited about that. The next one is electronics, right? Electronics is notoriously challenging in space. A lot of the systems that we build, there's always this criticism, right? Well, the space industry is using processors that are 2, 3, or even more generations behind the state-of-the-art that we use on the ground for commercial applications, so on. So how do we address that, right? So we're going to continue to try to harden by design, to use redundancy, to shielding. All of those tools, right, are going to continue. When you hear about bases on the moon, on Mars, and so on, yeah, we're probably going to keep some of our computing electronics resources shielded underground, perhaps, and so on. But what we're doing here is we're not discounting all these other approaches. What we want to do here is take a parallel path and look at a radically different way to do electronics, right? To do electronics for space. And what we envision here is an all carbon nanotube-based avionics for space application. Why? First, it's inherently radiation hard, so that's a big motivator right there. Second, it's low power, it's non-volatile. And third, it can be stacked up in multiple layers. So it allows for very, very high density, very compact system on a chip kind of concepts. The picture on the left is a wafer and a packaged memory device, we call that NRAM, that is entirely carbon nanotube based. We built it, we tested in the lab, and actually this one we've flown. We demonstrated in space. Well, memory alone won't do it, so the picture on the center, so where we are with logic devices, right? So these are carbon nanotube based field effect transistor that have high electron mobility, comparable to silicon. We've demonstrated this one in the laboratory. Now you have the memory and you have your logic devices. Now you can start thinking about system on a chip as indicated on the right. And again, as I said, this can be stacked in the third dimension, leading to very high density electronic systems. We believe this will be part of the solution for long-term exploration of space, either deep space or Moon and Mars. So now I'm going to shift gears and I'm going to talk about defense. And so what's pictured here, right, is maybe a missile defense systems. Again, this spacecraft has no solar arrays and so on. So this is a nuclear powered, high energy laser system. And you can imagine that this technology has dual use, right? The nuclear power and being able to beam a high energy control and beam high energy laser system can be used as a power distribution system, right? You're going to see that I'm going to allude to that back then. But with the challenge with this area, right, is the threat is always evolving, right? And we hear a lot on the news and so on, hypersonics, and it's not only very fast, right? And now it's maneuverable too. So it's, just gets more and more complicated, more and more challenging to track that and to defend against it, right? So what's going to come to help, right? In 2050, we really believe we're going to have fully integrated air and missile defense. And even though the problem and the challenge is growing, is going to grow on the time frame, is going to get more challenging. What's going to come to help us are these novel sensors, right? And we talked about quantum communications. That technology is very transferable to quantum remote sensing. We're working on that too. The interferometric imagers, and then the ability to bring multimodality sensors, right? The radar, the optical, the IR, multispectrum and so on, and being able to bring all of those and use machine learning and so on to find patterns, right? And allows us to detect and track threats early on. So that's the sensing piece. You've got to start there. You need to be able to sense. I'll talk a little bit more about that in a second. Second is what do you do about it, right? So we're not trying to say that directed energy will replace kinetic intercept and so on. We believe in a layered defense system, if you will. Those are going to continue, but we believe this will be part of our solution space here because you can act at the speed of light, right? So that's what's illustrated here. A couple areas that I want to expand upon related to defense, right? First is phenomenology. So what does that mean, right? It's what is the phenomenon you're trying to observe, and then what our team is doing here in this area is basically trying to answer the question, what does nature allows us to observe, right? So you need to have an understanding. We've been doing this for decades, right? We're really good at this. What's different? There are two things that are different here in the past few years. Historically, this is really a physics, chemistry-based approach, right? It's fundamental, right? What is the phenomena? What's happening? What's on the plume of the missile, right? What's the chemistry, this and that? And what can you observe? And what's the best detector technology? What's the best orbit? What's the transmissibility between the target and where you're observing and all of that? So, and that's very strong. That's very powerful. We're continuing to do that. What's happening that's new on the past few years with the maturation that we've seen in machine learning and AI and so on is the ability to use those technologies, right? AI, ML, to fuse data from sensors of multimodality sensors, right? So optical, multispectral, and radar, right? And be able to determine patterns and extract additional information. That has proven to be very useful. We're continuing to work on that area. So that's one element of what what we're doing here. The other element that is new over the past few years is, especially with the advancements that we're seeing in hypersonics and so on, we really took a step back and asked ourselves, again, the very fundamental question, what does nature allows us to observe? And what happens is for these very high-speed systems, right, on the hypersonics realm, what's happening is there's a lot of new physical phenomena that does take place that we hadn't explored in the past and that we're exploring now. So this is leading us to basically new sensor modalities, new phenomena that you can use to sense, detect, and track, and classify, right? That's the other aspect of that. So this is an area that is of extreme importance to us. So this is the sensing aspect of the defense. Now let me go back and talk about the actuation or action part of that. And I talked a little bit about directed energy. The picture on the left is the beam director for our Athena, which is this demonstration system. This is it's a trailer-sized system. It's a ground system. It has been very successful. It allowed us to demonstrate a multitude of technologies, and it allowed us to demonstrate them in a very realistic scenarios against drones, right? We were able to take out mortars and drones from small quadcopters to 12-foot wingspan, fixed-wing drones, and so on. So very successful system. The other thing that allows us to do is to experiment and demonstrate different laser technologies. And one technology that is very, very exciting now, and I'll try to connect that again with the power in space in a minute, is fiber lasers, so solid-state fiber lasers, right? They're robust, they are scalable. We've developed the technology to combine them spectrally to achieve the power levels that are needed for these kind of missions, right? And the picture you see on the right is the next generation of Athena, right? This is a much more, Athena was a demonstrator. LLD, Layered Laser Defense, which is the picture on the right, this is a product, right? This is, and it was designed to be very compact, much higher power. The algorithms also to detect, track, and engage, and to do the atmospheric beam compensation are more sophisticated because we learned on Athena and we reflected them here. This actually, believe it or not, does use AI, ML algorithms on it to do the target classification on them and choose the aim point. This system is designed, it can be incorporated on a ground vehicle, on a ship, and airborne. And with modifications, it could also be used as a power generation system for space with power beaming. All the technologies are built in here. So let's talk about exploration. And this is, there's part of exploration that is so interrelated with commerce and logistics that I'll talk a little bit about that too. So for exploration, this kind of time frame, we really see we're going to have a sustained presence on the moon. But what we really envision for Moon and Mars is a sustained robotic and human presence, right? We believe that autonomy, telepresence, human-machine interactions are going to be paramount for that. When you think about establishing a base on the moon and driving that kind of exploration, either scientific or commercial, there are some things that are fundamental, right? You need to have power. So what you see illustrated here on the bottom left of this picture is basically one of these nuclear power systems. I mean, it's beaming power to the other areas, so you don't need to be replicating this or laying cables and things like that. So power, communication, mobility, you need to be able to move around, right? With these three elements, you can then now seriously, incredibly start talking about in situ resource utilization, right? Because you're going to need to have power to process the materials and generate oxygen, water, and materials to build the structures and so on. So we believe in this kind of time frame we're going to be able to do all that. The picture on the top right here illustrates a propellant depot, right? That's an insert there towards the center. A power generation unit. That power generation unit is transmitting power, beaming power to a factory that is producing, materials, components, whatnot, things that make sense to produce in space. But that also doubles down as a power distribution system to other assets that might be in space. And really, between Earth and Moon, cislunar, and what we're going to learn on the moon, right? It's really going to lay the ground for us to really do a safe and credible exploration of Mars. So a couple things I want to share with you that we've been working on this area, right? So let's talk about this infrastructure. So recently we announced a service and a commercial partnership with General Motors for what we call lunar mobility vehicle. So those are illustrated on the left portion of this page. These vehicles, it's really a good combination, right? Because Lockheed, we have a lot of experience with space exploration, deep space exploration, asteroids, and you name it. And GM has, of course, tremendous capability, not only with now their investments in electric vehicles, but also autonomy, and as well as vehicles they've developed for the military. So when you look at that combined, this makes a lot of sense. So what we're doing here is we're basically this is also a different business model, right? Not only developing the system and the engineering of that, but also the different business model where this would be provided as a service, right? So if you have an idea, or a company has an idea to go do something on the moon and either science or commercial exploration and so on, mobility would be ready, right? It would be ready and available, right? These are some of the features of these vehicles that we're contemplating, that we're designing, are level 5 autonomy, right? So fully autonomous, ruggedized, right? We don't have roads yet on the moon, so you can truly explore the entire moon. Very long battery life, right? The moon, the night on the moon is like 14 days, very high extremes of temperature, right? At night, minus 280 Fahrenheit. During the day, 260 plus. So very large swings of temperature. So these vehicles will be able to handle all of that. A communication system, and I'll tie that up in a minute here with the right side of this chart. But a reliable communication system, not only to communicate between different points on the moon, right? Different bases or astronauts that might be exploring in a mobile vehicle and so on, but also communicating to Earth, right? So mobility is critical. Communication is critical. The picture on the left bottom here is actually a simulator that GM and Lockheed have put together to demonstrate this vehicle and so on. The vehicle can be operated by an astronaut, but it doesn't need to, right? So it's human optional, if you will. It has a robotic arm to help you load and unload the vehicle, right? So it transports cargo, it transports personnel, and it has long range, and it can basically operate through the long moon night. So very, very excited about that as a service, right? That will help with this infrastructure that I talked about. The right side of this picture here is Parsec. And Parsec is basically a commercial service that will provide communications, high bandwidth communications on the moon, and precision navigation timing, so also not geolocation, lunar location, right? To help you navigate and tell you where you are, where you want to go. And of course, these things go together, right? Because the vehicles are talking to Parsec, and if they're autonomous and you want to go from point A to point B, or you want to pre-position a vehicle, because from the gateway you're going to be sending an astronaut or cargo and so on, the vehicle can be, he needs to know where to go, right? So navigation on the moon. So not only communication, but navigation on the moon. We're very excited about this. This is going to be a system. Parsec is a system that's going to grow to multiple spacecraft. So we talk about LEO, like low Earth orbit. This is low moon orbit. This is based on our, we call it our small sat bus that we developed for deep space exploration. So all the characteristics and the reliability and design of the bus, including the avionics and all of that, is well designed to operate in this kind of environment. We're also using a SmartSat, which is something that we developed over the past few years. That is the concept of having a middleware on your spacecraft and then being able to upload apps to do different missions. So we're leveraging that too, as well as an automated mission planner. So that's the reason we're going to be able to pull this together relatively fast, and we're aiming to have the first few nodes around the moon in 2024 to grow after that. Again, very different models here to provide and put this infrastructure in place. All right, so I talked a lot about exploration on the moon and maybe cislunar and so on, but one of the things that we need to continue to do and is deep space exploration, right? And I talked to you about OSIRIS-REx, And here, what I'm illustrating on the right side of this chart here with the pictures is Europa, which is one of the moons in Jupiter, where we believe that there is an ocean, right? The structure of Europa, that's what's shown in this picture here, that there is an ice crust covering, and there is an ocean where there might be life, right? So there is a lot of interest in exploring ocean worlds, right? In this particular case here, Europa. And one of the things that we kind of know, but then we also learned, is on OSIRIS-REx. As we learn more about the Bennu asteroid, right? Originally, we thought it was a relatively smooth surface. As we learn more about the asteroid, we learned that the surface was extremely irregular with a number of boulders the size of the White House, right? So that was, of course, of large interest and severe implications for the success of this mission of collecting a sample, because the spacecraft needed to pretty much touch the surface to collect the sample. And the original system that was doing that was a LiDAR system, a point-based measurement, so not very robust because it doesn't give you situational awareness. That's why we transitioned that natural feature tracking technology that I mentioned to you, because not only it gives you all the information to do this sample collection maneuver, right, to do the relative navigation, it also gives you situational awareness. It can basically map the surface of the asteroid, right? So we learned that, and we had to change gears on the technology we were going to use for that. So we adapted natural feature tracking to do that. Very successful. Check. The other thing we learned, that one was actually during the sample collection maneuver, is that the surface of the asteroid was much softer than what we thought it would be. And as a result of that, the arm went in about a couple feet, right? Well, you could have lost the mission by that. The control system had enough gain and phase margins that it could compensate for that, so it wasn't a problem. The point I'm trying to make is that when you go do this kind of explorations, right, we're going to use the best knowledge we have of the systems we're going to explore, of the environment, but there are a lot of unknowns that we're going to encounter. And what we need to do is really to be designing systems, because the travel time or the communication, you can't really have the human in the loop on all of that. It's not practical. You need a high level of autonomy. So we need to design systems that are inherently robust and adapt to the environment as they find it, right? So what I'm showing here on the top left of this chart, right, is causal and reinforcement learning, which is work we're doing jointly with JPL. We're very excited about this. This is truly using deep learning, AI techniques, right, to using the best model we have of the environment, plus what we're learning in real time, to be able to adjust to that and drive action. So this is taking autonomy to a whole new level, and this is enabling not only for this very deep space exploration, but even if you think about Moon and Mars, it is very likely we're going to find a number of situations that is not, we couldn't really predict, that we're going to learn. We want to learn in real time, adjust, and compensate for that. So the last area that I'm going to talk about is, I really want to talk about Earth, right? Because we're so focused on space, and I love it, right? There's space is cool again. There's renewed interest in space. This is very good for, for the space industry and for humanity, frankly. But at the end of the day, if we have all these sensors that we're talking about, right, in terms of remote sensing, that we can truly monitor in a global scale and constantly what's happening on Earth, and we have this robust communication system and so on, we can actually use a lot of that information to benefit Earth, right? So think about helping Earth. So resource utilization, fighting man-made or natural disasters, right? Responding quickly to those. Climate change and so on. Having a better understanding of all of that and being able to use and truly develop systems that can use all this information that we're collecting to benefit the environment, it's going to be a major area of development here. The other piece, which is shown on the right, bottom right of this picture here, is the concept of smart cities, but really smart worlds, right, beyond cities, right? And it's the fact that when you look at a number of things that are happening with Internet of Things, and autonomous mobility, right, starting with cars and so on, but we're also talking air mobility, and there's a lot of investment in terms of air mobility, and as the numbers increase, if we're talking 2050, that kind of time frame, this is going to be commonplace, right? So being able to have the sensors that monitor all that in a very reliable way and then provide the information is paramount for these systems to work properly. So the example I want to give on this one, we call it GeoHealth. The blue picture on the left here is actually a picture from one of our instruments. It's called GeoLightning Mapper. So it's an instrument at a geostationary orbit on the GOES spacecraft that monitors lightning. So why would we want to do that? Well, scientists found that when you see an increase on intercloud lightning, on the frequency of that intercloud lightning, that is a good cue, there is a good correlation here that you may have the onset of a tornado, right? So we developed this system for NOAA to increase the warning time for tornado from what used to be about 5 minutes to about 30 minutes, right? Saving life and property. So very, very useful. So this is one example, right, that we're doing now. Now, these kind of sensors can be used for a number of other applications. In fact, detecting lightning, because the duration is so short, is much, much more challenging than detecting fire. So the spectrum that I'm showing there, and I think it's on the IR band, is of a fire, right? And so what we're doing right now, we called it firefighting information as a service, right? Is really leveraging the remote sensing capabilities we have now with the integrated communication systems that we have now, and developing smart agents that pull together all this information and provide really timely and a bird's eye view information to the command centers and firefighters in fighting fires, right? So what's important when, for the firefight? Well, they need to know the perimeter of the fire. They need to know which direction it's moving. So think about the sensors we have, right? We can detect where the fire is, we can detect the perimeter, we can measure winds with LiDAR systems, so we can also measure with hyperspectral, we can measure humidity content on the vegetation, so where do you have fuels and so on, so you can really now predict, this is the perimeter of the fire, this is the direction it's moving, this is how fast it's moving, right? You can predict where it's going to go, and you can deploy resources. Unfortunately, we don't do it this way today. Today, it's very manual, and people getting on the phone or sending messages and so on, so you lose a lot of precious time in being able to contain this. So the example here is for fighters, but we see this using this kind of information to improve the utilization of resources and to deal with disasters is a whole new area for growth that will truly mature, and this won't take until 2050, right? We're actually doing it right now. We call our agent, our command control center, we call it AI forward for this particular system here. So with that, let me end where I started with Space 2050, and I want to end with a call. I mean, this is all sounds cool, but it's also very challenging, right? Nobody's going to do this alone, so it needs all of us to make this vision a reality. So let me ask you all to join us. Either join our team or join as a partner, right, from your organization, so on, because it's going to take all of us to bring humanity beyond Earth. Thank you. And we have 6 minutes for questions, if there are any. Oh yeah, if you haven't seen yet, I recommend you stop by and take a look at Callisto. This is our AI agent that is going to be on board of the Orion spacecraft, and it's in partnership with Amazon and Cisco. It's just down the area where you do your check-in. Thank you. Oh, okay.
Hi, thank you very much. I had a question about the transference of energy via the lasers that you have in a couple of different use cases. If something interrupts one of those beams, is that enough energy to burn a hole in something, or what's the concerns about that degree of energy being passed?
Yeah, so the question is for the power beaming, if something interrupts the beam, right, is this a problem, right? Is that something going to get damaged and so on? So first of all, I'm going to state the obvious. It depends on the energy level of the beam, right? It also depends where you interrupt the beam, because for the examples I gave you for directed energy, you're focusing that beam on the target, right? So if you're interrupting the beam in a different area, yeah, there's still a lot of energy there, but depending the exposure time, it may not be catastrophic. But for these systems really to work, where you're doing power beaming and so on, we see a power distribution system, right? Maybe one large beam, and then you distribute with much lower power beams. It should not be a huge problem from that sense. It's more of a concept of operation, how you want to operate it. The other piece of this is that's where the whole level of automation comes into play, right? Because you would design this so that they wouldn't be interrupted, right? You don't want anybody flying through that beam. Yeah. Uh-huh.
Regarding communications, so I have two questions. What is the bandwidth that you envision and the speed of the communication? Because, I mean, communication I think is critical, right? And
Right.
because we are talking about big distances,
Right.
bandwidth and speed.
Yeah, with this technology in the 2050 time frame, we believe terahertz is possible. Yeah, we're not going to start there, of course. What we're doing right now in the lab is much lower than that. But the architecture is very scalable, right? Because we can truly increase the information density. What I mentioned to you, bits per photon. Yeah, it is way beyond what we can do today.
And what about the speed? I mean, how fast can a message get from, let's say, the moon or Mars?
Speed of light. Speed of light. We haven't been. Yeah, speed of light. Yeah.
Oh, so that's the plan.
Right.
Speed of light.
Yeah. Okay.
More in the back here.
Yep.
What's the biggest hurdle to generating power at that scale in space?
I think the biggest hurdle would be more like political, right? Right now, when we look at all the different technologies, it's nuclear power seems to be a very good option for everything we're trying to do. So we just need to think through how would we do it, right, in a safe manner. But there is a lot of I guess misconceptions about nuclear, and there's a perception that is dangerous and so on. And I'm not saying it's not, right? As we've seen, there's been accidents and so on. But we've proven, when you look at what the history of the aerospace industry in particular, right? Nothing that we do is really easy, right? Things are challenging, and we've been able to the appropriate thought process and putting the right engineering, the right process in place to do it in a safe manner. Yeah, those are my thoughts on that. Yeah.
Probably the last one for me. What about the materials that you're using? Where are we going to get those from?
The materials for
To build all this stuff.
the lunar.
Yeah, to build all of the spaces.
Yeah, so this would have to be in situ resource utilization, right? So we would need to be able to use, it's not very practical if you're having to haul everything from Earth, right? We may have to do that in the beginning, but as we learn more on how to utilize the materials from the moon itself, from Mars, from asteroids, we should be able to shift our use to basically local materials, right, on the celestial bodies that we're going to be exploring. Yeah. Any other questions? All right. Thank you all.